much for being here, Ravenpack. Thank you very much for having us. It's a pleasure. I had the opportunity to be here last year as well as an attendee, so it's an honor to speak to you. I wanted to say a few words about Unigestion. We are a specialized asset manager with $23 billion under management in public equities, private equity, and liquid alternatives cross-asset. And I will present to you some applications that would fall into the public equity bucket. So maybe a bit of motivation how we got to this topic. So after following this space for a couple of years, one of the things that I noticed was that a lot of speakers pointed out that we are struggling with relatively low signal-to-noise ratios in finance, but we still apply these very sophisticated tools to it. So what we thought, well, why don't we look at something that is slightly easier to forecast, something more persistent, which is risk. So what I want to speak about to you today is the issue of forecasting stock beta. And doing that using both Ravenpack equity sentiment data as well as some of the machine learning techniques that a lot of you are familiar with. And the results are, in a sense, humble. So I will show you some statistically significant improvements, but economically speaking, they're relatively small. And that's how I personally like our research innovations. As opposed to having one magical improvement, we like to have a sequence of small but statistically significant improvements that overall diversify themselves and give us robustness. And I wanted to also start off with this quote. Some of you may have read the book by Nate Silver. He was famous for having forecast baseball scores very successfully, and then also, I think, 48 out of 50 state elections during the one of the recent US elections. And he wrote a book called The Signal and the Noise, and he said we need to stop and admit it. We've got a prediction problem. We love to predict things, and we aren't very good at it. And the reason why I brought it up is that when I looked at some of our attempts as a community to forecast expected returns, so first moments, very hard thing to do. Doesn't really work so well, but sometimes we claim they work well, and then when the authors were asked whether they actually use these results in practice, they said humbly, no, not really. So we tried to look at a problem that was a little bit more suitable. And for illustration, what I brought up here is just this difference between forecasting expected returns or mean returns as opposed to risk. So we've plotted here the Apple monthly return over time. And as you would expect, it's highly volatile. It goes through positive and negative phases. And the vast machinery and literature that I'm familiar with, both from practitioners as well as academics, they've actually tried to tackle this really tough problem, forecasting average returns for stocks or asset classes. The results, when one looks at them, I was invited to discuss the paper by Giuliano Rossi and his co-authors back then, so this is officially a paper by Macquarie, was that when one takes some of the machine learning tools, unsupervised and supervised learning, and applies them to one country and then takes the same hyperparameters and applies them to another country, they don't work so well. So in other words, we can get, for certain specifications, very impressive results, but the question of robustness arises. Now, why is that to be expected? Because the signal-to-noise ratio, of course, is relatively low, and you've been all in the past presented with examples from the physical world where there are very high signal-to-noise ratios. But there is one variable that is generally a bit easier to forecast, and that's also the bread and butter at Unigestion, which is the forecasting of risk. It's very important for example, hedging, but also portfolio construction. And Apple's alpha is volatile, but it is more persistent, as we know, as a variable. Second moments are more persistent than first moments. So what we asked ourselves is, could we do the following? How would it work to forecast risk as opposed to average return using some of the machine learning algorithms that you're familiar with? So I would say that we are not innovating in terms of the algorithms. Most of you are familiar with them and have them available through various toolboxes. But we apply it to a different dependent variable, and we use also the Ravenpack news volume and equity sentiment variables. So for those of you that are less familiar with this area, here just an example. Here we've got Apple news stories over time, as an example, 2017 to 2017 January to December 2017. And as you see, there's a bit of a peak around September. Maybe just a show of hands if you think you know why there is a peak in September 2017. Okay, I'm just checking whether you're still paying attention. So I think you may be right. It's not the iPhone. It's actually the Apple Watch. So it was released around September 2017. Of course, there's a news cycle. I finally succumbed last year to it. I bought one of these, quite happy. But you see it sort of shows up in the news volume. And what you also have is you've got sentiment, which would be a number above 50 if it's positive and a number below 50 if it's negative. This gives you an idea of our raw material. So this is one of the signals that feeds in. And what we then looked at is we asked ourselves, is this big data variable, these two big data variables, if we combine them with other fundamental variables, can they somehow help us forecast beta better? And before we get into that, let me give you an overview of the cross-section of variables that we look at. What we've done here is we've just standardized the variables. So the lowest value would be 0 and the highest 1. And we plot the cross-section and then Apple's value, just to give you a sense for whether the magnitudes make sense. On the far right, if you look at it, it says 1. As you would expect, Apple gets a lot of news. News volume very high relative to the other stocks. In terms of market cap, it's also a very high stock. If we plot the mean market cap relative to the whole range. And these are some of the financial ratios that we use. It's just a small subset. In fact, we've got several hundred that we use internally at the stock-specific universe. And we then try to forecast beta. And to briefly summarize our results, so we do find that adding fundamental variables helps us forecast beta. Secondly, we find that among the different types of algorithms, tree-based machine learning algorithms work quite well. So far, we found that actually neural networks are not that successful in this particular application, and we implemented the XGBoost algorithms in Python, and that's particularly one that has performed relatively well. And we find that within the list of variables, Ravenpack stock sentiment is a variable that is statistically significant. And I'll also show you how the significance changes over time, because that's an important question that arises, right? Why does this algorithm work? And one can dig into it in more detail by looking at the importance over time. Finally, something that wasn't completely surprising, but still worth noting, macro variables as interaction terms were not useful. Some of you may have followed the research on expected returns in stocks and expected returns in bonds and the references that I brought up. And one of the things that's done there is you've got bond and stock-specific cross-sectional variables. And then you say these variables may change as predictors depending on what macroeconomic cycle you are in. So you can interact them with a time series variable called a macro variable. And we found, though, that in this application, when we looked at it, the macro interactions don't add much more value. They do add value in a paper that I cited when it comes to bond return predictability, but not in our context. So let me show you the details. And one important lesson to bear in mind is here, the best qualification of a prophet is to have a good memory. That's important to bear in mind, because one of the best ways of forecasting beta is just to look at historical beta, right? It's quite persistent. So the logic is twofold. We say it's a variable that's easier to forecast, good, so potentially a higher signal-to-noise ratio. However, you've got a very strong horse in the race, which is just the historical beta. And in a first step, what we've done is we've looked at a lasso regression just to look at the statistical significance. So that's a way of model selection that has advantages over simple stepwise regressions. And we find that, for example, the Ravenpack news volume is positively related to future risk. And in a statistically significant way. So this could be interpreted as news volume goes up, risk goes up, maybe some of this news volume is negative. That would be one interpretation. And when we look at average sentiment, it's negatively related with the future beta. So as sentiment improves, the beta goes down in the cross-section, which could also be potentially interpreted as positive sentiment being good news, and that leading to a reduction in the stock-specific risk. When we then look at several metrics of performance, in terms of out-of-sample performance, we look at accuracy. So how often can we predict the future value of the variable and how often is it correct? And we look at just simple linear prediction. So a useful way is to ask all this fancy nonlinear machinery, does it add any value? Or can we forecast better with simple linear models? We've got standard error bands around them, and as you see, the random forest and XGBoost algorithms do give us, on average, better out-of-sample predictability. On the right, we've got the one-year rolling accuracy, and when the orange line, which is the random forest, and the red line, the XGBoost, is above the blue line, that means that it's statistically significant because we have a blue line, which is the linear model with standard error bands. So we've got a confidence interval around it, but we also have to admit that it's not always the case. So there are some periods within the sample where the simple linear model performs better, but on average, it does work well. Now, if you are differently minded, you want to look at R squared, so this is just a different perspective, or the average correlation between the future value and the predictive value. We find that the XGBoost gives us a better forecast of the future beta. Similarly, the mean squared error is lower when we look at the ability to forecast stock-specific beta. We see again that we get a statistically significant improvement relative to a simple linear model. And finally, here is a slide that summarizes the interaction terms. There are 8 lines. 4 of them are without interaction terms, and they are the 4 models that I presented to you, and 4 of them are with interaction terms. And when you look at the accuracy, adding macroeconomic predictor variables doesn't really move the third column value significantly above what we would get with XGBoost without interaction terms. Here we have predictor variables over time. So one of the interesting questions is, okay, how can we open the black box? How can we shed more light into it? And we see that certain variables, such as price momentum, is an important variable throughout. That's one of the variables that we use. But in terms of the Ravenpack variables, on the right, you see the yellow line, which would be the news volume, which plays a role from the very beginning, but sentiment only starts to play a role later on, which is something that we're discussing at the moment, and we're looking to speak to you about after the presentation as well. But here we see how the algorithm chooses the different variables in terms of their importance. So to summarize, we find that we can forecast fundamental so we can forecast beta using fundamental variables and sentiment scores. Interaction terms are not important, but we do find statistically significant improvement. The economic value of them is small, but they are statistically significant. So now we've got a minute for questions.
Thanks very much for the presentation. I'm just wondering, your target in this case is beta, which is obviously sensitive to the window length that you use to estimate whether it's historic or forward-looking. So I'm just wondering how robust your results are to changing window length.
That's an important question. So where we came from was the notion of relatively infrequently rebalanced portfolios, because this is something that we sort of see as an application in practice. So we've looked at 1 year and 3-month betas, which is what we looked at, as opposed to relatively high-frequency predictions. So there are other results there with implied and realized betas, but they would really apply to relatively shorter horizons. Well, we know that from the kind of public equity portfolios that we rebalance, they wouldn't rebalance very frequently. That's a good point.
Robert, we have time for one more question. Your choice on the screen. Slido questions here. We've got 2. Which one would you like to answer?
Well, let's maybe take the second one. The question of whether there are fundamental reasons why tree-based models work better than neural networks. I think that my own interpretation is that in neural networks there are quite a lot of hyperparameters to choose, and eventually one can get the data to confess, but in my experience looking at different applications, there is some sensitivity to the hyperparameters. So I think that sometimes some simplicity may also be useful. That's as much as I can say on that at the moment, but we are still exploring different algorithms. Of course, it's always work in progress.
This is Raven Pack.